All right, guys. So welcome to Antimatter's first internal workshop. We're calling this Workshop Zero because, again, it's an experiment for us in terms of how to carry these workshops on, and kind of how to modify the delivery mechanism to make sure, and in terms of topics. And so the topic that we're going to be covering today is real-time client-server communication, and more so, we're going to be focusing on the evolution aspect of it. So, I know that most of you may have kind of worked with some modern technologies in order to, achieve this, but it's also kind of it's also important to understand where we came from. Why do we have these modern technologies? What did the primitive technologies lack, which kind of caused engineers to build these modern technologies. Now, before I talk about the topic itself, let's just quickly understand what the purpose of these workshops is, because this is the first formal one. So, at the very core of it, we do want to improve interaction between engineers, because we kind of have received feedback that fully remote engineers often feel that they're cut out from the rest of the company. Those of us who come on site, we do interact with each other on a regular basis, and we there is some sort of knowledge transfer that way, but fully remote engineers often don't get that chance. So this is kind of a just an approach to maybe help improve that. And then obviously we're going to be delivering valuable information. Duh, that's the point of these. And these can be both technical and non-technical. We're still trying to figure that out, in terms of which side you want to lean towards. But it can also be a combination of practical examples and theory. And obviously, the most important reason is I really need a raise. So I hope that HR is watching this as well. Anyways, so this is going to be a theoretical one, and I apologize in advance. Please bear with me. We'll get through this. The original plan was to actually involve an AI agent in this process, and so it made sense to have a very theoretical topic that the AI agent could handle as well. But we had to scrap that idea, and we did still have the content. So we were like, well, why not? Let's just deliver it ourselves and see how it goes. And I know that a lot of engineers here probably have worked with something like a WebSocket before, but I think it's not unfair to say that a lot of us often lack theoretical understanding of how these technologies work under the hood. And if you're building features on a day-to-day basis, it might not matter that much. But when you really need to optimize features, or when you're stuck on some sort of deeper problem, that's when this kind of theoretical knowledge does actually become useful. So let's talk about the problem itself. The problem is very simple. We just need to establish real-time communication between a client and a server. And this kind of functionality is what you would typically need if you were building something, that required live updates. So for example, live weather updates, or, real-time analytics. Think about like cryptocurrency price trackers, or stock price, trackers, things like those. Chatting and messaging, that's where you'd need this as well. And something like real-time collaboration. So collaborative whiteboarding software where you can see each other's pointers, and it's all happening in real time. Now, in the first case where we have live updates, in that case, the communication would mostly be unidirectional. So the server would be pushing data to the client. But in the third example, the example of real time collaborative whiteboarding, that's where you need bidirectional communication in that case. So ideally, whatever solution we work towards, should be able to cater for bidirectional communication as well. Now, the way that this workshop is going to go, we're going to start at the very bottom. Identify the problem. We'll think of some primitive solution, and then we're going to examine that solution in terms of its pros and cons, and then keep building up from there, and eventually kind of land on something that's very modern and very usable. So before that, I just want to give a bit of context, because again, I know that most of us here might be familiar with this, but some of us might not be. So we know that the traditional web operates on a client and server communication model, where the client initiates a request for a particular resource, or some specific data, and the server finds that data, finds that resource, and then returns the response right away, and the connection is closed. That's it. And this is all done over the HTTP protocol. So again, for some more context, we can break down networking into 7 layers in the OSI model, but this is an even simplified model which has 5 layers. And HTTP is the very top layer; it's the application layer. And for some more context, HTTP works over TCP. So we have the application layer, that is layer 5, and this works directly on top of layer 4, which is the transport layer. So, in the context of networking, where you have, let's say, a device A connected to a device B, you're going to have a lot of intermediate devices, intermediate routers in between. And the lower layers, so the network layer, the data link layer, and the physical layer, those are going to handle communication between those intermediate devices on a device to device. You can think of this as a hop to hop basis. But the transport layer, that is responsible for the end to end connection. So if I'm connecting to a device, my device A is connecting to a device B, that end to end connection is maintained by the transport layer. And this is again important because we're talking about HTTP in this context. So TCP, for those of you that aren't aware of this, all that you have to know is TCP is a reliable protocol. It kind of enforces, rather guarantees message delivery. And there's this idea of handshakes and acknowledgements. If I'm sending data to device B, I should expect to receive an acknowledgement from that device that it has received the data that I've sent it. So this is where I just kind of want to ask you guys. Let's just, given the fact that we know how HTTP works, can you guys maybe think of a very, very primitive, we could even call it dumb, a very dumb solution to, get some of that real time data communication. So please drop your messages in the chat. So this is what we would call short polling. Basically, the idea of just spamming HTTP requests. And this works. It's a terrible approach, but it does work because the idea is, as soon as you receive a response from the server, you send another request, and then you send another, and repeat the process. And the idea is that you should eventually be able to, retrieve data as it is being updated on the server side. I think it's fairly obvious that this is not a good solution at all. And the reason that it's not good is from a client's point of view. If we talk about like JavaScript, you would be making, just Axios and fetch requests over and over and over again. So there's load on the client for no reason. But more importantly, the server is under a lot of load, and as your application scales, and if you have tons of clients doing this, it's not going. You're going to pretty much overload your server. The network is going to become congested, and the reason for that is HTTP. There's a lot of HTTP overhead when we're doing with something like this. And that is, it has to do with the nature of HTTP itself, and the fact that, again, HTTP, it operates on that request response model. So eventually we would have to deal with high latency, and connections would drop. So we've already lost that real time aspect. And so I was talking about HTTP overhead. That is because of the TCP handshake itself. You're creating a new request every time. That includes a TCP handshake. That includes domain name resolution, and you're also sending a full set of HTTP headers. And this overhead is usually it's going to be around 5 to 7% of the actual data you send. So it's pretty bad. Let's move towards our first solution. I think we've identified that the first step that we need to take is reduce the number of requests, limit the number of requests that we're actually sending from the client side. So no short polling. And that's where long polling comes into play. So the idea is the client sends a request to the server, and instead of responding right away, the server holds that request open. It keeps the connection open for a longer time. And again, this would, if you were doing this in the real world, this would be custom implementation logic. But usually, the logic on the server side is, do I have any new data that I can send back to the client? If I do, then you should send the data back. The request is closed, and then the client initiates a new long polling request. And again, the server keeps it open and just kind of waits to see whether the data source has incurred any changes, and the process follows. So this would entail custom implementation logic. But one way would be to use the event emitter, for example, and you could, if you had a data source, you could bind it to an event emitter, and that way you would know, when your data source is actually changing. So again, so one potential problem that we have here is something of this scenario here. Uh, so the important thing to note here is the client initiates the request, not the other way around. So, let's say we have a data source, in this case, these numbers that are changing from 1 to 2 to 3 to 4. There's always a possibility that at some point in the process, the client did not initiate the long polling request, quick enough, or something, there was an error, something, the request dropped, halfway. And so you may end up, missing data changes, as they're occurring. And from a kind of feature point of view, this would lead to like jittery behavior on the client side, because you're missing data as it's changing. And the thing is, I mean, we have reduced number of requests that are initiated from the client, but we still have the problem of HTTP overhead. And again, this approach, given this scenario here, we're going to be seeing latency, and we're still not close to that, real time communication that we're trying to aim for. So this brings us to our next solution, and from long polling, I think it becomes obvious that, well, okay, what if we, find a way to not close those connections. So, even after the server, returns a response, can we somehow, keep the connection open? And again, this is not something that the HTTP protocol was originally designed for. The idea was, as soon as the server finds the requested resource, it returns it, right back. But again, we can exploit that. So in the HTTP 1.1 specification, that the first official specification that was published for HTTP, there was this idea of chunked transfer encoding. So you could basically, in terms of HTTP headers, there was a header that you could specify, chunk transfer encoding, and the value for that would be chunk transfer encoding. And the idea here is, so the way that this works is for normal requests, when you're in a normal environment, your client is sending a request and your server's returning a response. The server always tells the client, what the size of the response is. There is a content length header that includes, which actually includes the value, the size of the data that has been returned. The purpose of this chunk transfer encoding header was in cases where the server does not know what the size of the data being returned is. So, you could have cases where data is being generated randomly and you're not sure what the size of it is. That's kind of what this was meant for. But we are exploiting it here. So what we can do is we can keep our connection open indefinitely, and we can keep returning data, live data, real-time data in chunks. And the way that these chunks work on a theoretical level is, so for example, if we have this string, antimatter in chunks, the format for chunks is the first line specifies the size of the chunk itself. So in this case, we're returning 4 octets. This is text-based data. So that's why we have 4 characters here. In the second chunk, we now have 11 characters, this is a hexadecimal character. And so we're returning 11 characters here. And what this would actually look like is we would just, indefinitely keep returning chunks, even if the data was not changing. So in this example, our data source, this value, the second value here, it's still 1 all the way across. It doesn't change until we hit the 4th chunk. But because we can't keep, because we have to keep our connection open, we're just going to keep, returning that data, even if it's not changing. So technically, we have kind of solved the problem at hand, because as soon as the data changes, our client gets it. We're kind of guaranteeing that it's not going to miss the data as it's changing. And this is more efficient than long polling, because we're not repeatedly opening and closing connections. It's a single connection that's open indefinitely, and we're just dumping data into it. The problem here is that, again, this would again entail custom logic on our side, and we would have to handle things like reconnection ourselves. So if the client disconnects, there is no way for the server to know why exactly it's disconnecting, or what data did the client receive before it disconnected. So we're going to have to implement some logic on the server side now. And another problem that we introduce here is called back pressure. So back pressure is basically when our server is producing data, it's sending data. Because again, keep in mind this is a continuous data stream. It's not a request that's opening and closing. It's a continuous data stream. So in cases where our clients cannot process that data that fast, we would have to then implement, some sort of buffering mechanism, some sort of, intermediary ourselves on the client side. And not all clients are going to be able to support this. And again, the biggest problem here is this is not a bidirectional protocol. And if we wanted something bidirectional, we would have to develop some other sort of workaround where, let's say the connection from the server to the client is via HTTP streaming, but then the connection from the client to the server is via, normal HTTP requests. And again, it's not optimal. And as your application scales, it's basically going to break apart. And in fact, in the HTTP2 specification, the newer specification for HTTP that came out in 2015, uh, this header, transfer encoding header, was disallowed altogether. And the reason for that is HTTP introduced newer mechanisms, more efficient mechanisms for data streaming, and so there was no need for this workaround. So before we kind of before we take one step further, I'd like to take one step sideways and talk about one kind of modern approach that HTTP that is built on top of HTTP2, and I think most of you may have heard of this. And this is what we call server sent events. So this is a standardized API in the HTML5 spec. So modern browsers, all support it, and it is built on top of that primitive HTTP server streaming that we just discussed, but it's a bit more mature, and it utilizes UTF-8 encoding. So this is primarily for text-based data. It's not natively meant for binary data. There is a workaround for that. I'll get to that. But because it's standardized, it's very easy to implement. So all you have to do is use a special MIME type, or special accept type, which is text event stream. And this basically, from the server side, the response is, first of all, it's event based. This is an event based architecture. So processing can be done asynchronously, and this kind of SEC has predefined standardized fields, so that again, because like I said, this is a standardized API. So those fields include the ID field, the event field, and then the data field. So what happens is, unlike HTTP server streaming, we're not going to be sending data kind of indefinitely. We're only going to send data when it actually changes. And again, this is an event-based architecture. Another optional field that we have in this case is the retry field. And in this case, the server explicitly tells the client, what to do when when the connection is dropped. So reconnection is built in. That was, if you recall, that was one of the problems that we had with primitive HTTP server streaming. So again, automatic reconnection. This fixes one of the problems that we previously discussed, and it's standardized. There's a standard set of predefined fields that you're supposed to use with this. It's very efficient. Like I said, it operates on an event-driven basis. You're not just randomly, blindly dumping data, and it's very simple. It's quite simple. And SEC, again, it's very widely used in terms of modern web development. It's not unfair to say that it's probably the best solution when you need unidirectional real-time communication. Again, this is one of the main drawbacks here. Just like server streaming is, this is not a bidirectional protocol. And if you tried to do SEC two ways, from the client to the server and the server to the client, it would be a hot mess pretty much. Also, as I mentioned before, this is primarily for text-based data. So any binary data, like image data, would have to be encoded into a text-based format. So that's usually base 64, and if you were to encode binary data using base 64, you would incur a 33 to 37% overhead. So again, in terms of scalability, probably not the best thing. All right, so so far we've all the protocols, all the solutions that we've discussed have been built on top of HTTP. So maybe an optimal solution, we can drive an optimal solution if we ditch HTTP altogether. That kind of seems like the logical conclusion here. And that brings us to the glorious WebSocket, which I think most of you are familiar with. So the WebSocket provides us with a full duplex, i.e., a bidirectional communication channels over a single persistent TCP connection. And what's important to understand here is the WebSocket is actually, you can think of it as a replacement, not exactly a replacement, but in terms of the 5-layer model, it does operate on layer 5, so on top of the transport layer. So it kind of ditches HTTP altogether, and it operates by itself on over TCP. And the key thing to understand here is this integrates, WebSockets integrate very easily with existing HTTP infrastructure. And the reason for that is the ports that it uses are the same as HTTP. So HTTP uses port 80 for HTTP non-encrypted communication, and then port 443 for HTTP encrypted, HTTPS over so HTTP over TLS. And WebSocket does the same. It uses those same two ports. So the way that this works is your client would send a request, an HTTP request. In fact, the first request has to be an HTTP request, and the idea here is you're basically telling the server that, hey, I want to upgrade to the WebSocket protocol. And there are a couple of other fields that I'll explain in just a second. So you send the HTTP request, and you include these fields here, and the server then sends a HTTP 101 switching protocols response back, which is kind of an acknowledgement that, hey, we're now switching protocols, and kind of, you can think of this as like the initial handshake process is complete. So in the initial request, the client has to include a WebSocket key. And this is a random string of 16 characters that we encode in base 64. And again, this is generated randomly for every WebSocket session. So this is sent to the server. And then what the server does is WebSocket servers have what we use a GUID. So think of this as like UIDs that you work with, when in the context of databases or whatever. So a GUID is a unique identifier, but the difference here is everyone knows this. So for WebSockets, there is a predefined GUID that is actually publicly available in the WebSocket specification, in the WebSocket RFC. And so what you do here is you combine the WebSocket key from the client, sorry. You add the GUID, you append the GUID to it. You take the SHA-1 hash of it, and then you base 64 encode it once again. And you send this back to the client. And the reason for this is not a security mechanism. It's more just to make sure that the client knows that the WebSocket upgrade has been done successfully. Because what could actually happen is you may have some caching mechanism in the center that could cache this 101 switching protocol response. And so what the client does is once it gets a response back, it recomputes this value because the GUID is already known. So it recomputes this value, and that way it knows that its request has been received by a legitimate WebSocket server, and it's not receiving a bogus response from some random caching, like a reverse proxy server. It's not receiving its response from that. And on the server side, the reason for including this key is to make sure that no clients accidentally request an upgrade, a protocol upgrade. So it kind of goes both ways. And once this process is done, once the handshaking process is done, after that, that's it. You don't need HTTP anymore. Data can be sent. You're just sending your actual data in the form of frames then, and there is there's a very small header around 2 bytes that you have to include, and it's overall it's much more efficient than doing things via HTTP. So in terms of tooling, because WebSocket is quite standardized at this point. There is a WebSocket API for JavaScript, and so all WebSocket URIs they start with the WS or WSS prefix, and there's a lot of third-party tooling at this point as well. So you may have heard of Socket.io or Sock.js. These are very commonly used. Now, WebSocket has actually become the standard for bidirectional communication, and since the connection is persistent, we can simply send the actual data that needs to be transmitted. We're not having to deal with managing connections or request responses, HTTP overhead, headers. Not dealing with any of that. And unlike SEC, this has support for UTF-8, and it has support for binary data as well. So it can handle both of that natively. All right, so one bonus kind of solution that I want to discuss before we start wrapping this up is WebRTC, and this is it's a very new protocol. It came out back in 2020, and if you recall, WebSockets are built on top of TCP. This one actually utilizes UDP, and so since UDP is not a quote unquote reliable protocol, there's no sense of acknowledgements. You're able to send more data. There's higher throughput, but obviously it's going to come at the cost of reliability. And the idea is that WebRTC is a peer-to-peer protocol. So two browsers should be able to connect to each other without requiring any kind of server. But currently, in practice, you do need a server in the middle to set up the initial connection. And this has much lower latency, so it's really good for audio and video. But that comes at a cost of high bandwidth usage. All right, so since we were talking about HTTP, in general, I think it's good to talk about what HTTP is going to bring in terms of the future. So currently we're on the HTTP 2 protocol, which came out in 2015, and the next major upgrade to this is going to be HTTP 3. And this ditches TCP altogether, and it runs on another transport layer 4 protocol called QUIC, which itself is based on UDP. So again, the idea here is we want to optimize HTTP for mobile devices, because mobile connections are spotty. They're not as normal. Normal Wi-Fi connections are generally much faster. So you want something that is able to push out data much more effectively. And the QUIC protocol actually handles things like acknowledgement and resending packets itself. So it handles all of that. And the really interesting thing is, in terms of our context, so in the context of real-time communication, clients can actually skip the handshaking process for servers that they have already connected to. So things like long polling actually become a lot more feasible, because when you're sending subsequent long polling requests, the actual handshaking process is you can skip the handshaking process. So you're reducing latency, and it's in cases where long polling is currently not very feasible, it might actually become very feasible down the line. All right, so that brings this to an end. I want to keep this relatively short because I know that theory is kind of difficult to absorb, but we can maybe take some questions. I do see some questions in the chat, so I'll start getting to them. Can we implement streaming of audio and text at the same time through WebSockets? If yes, how? At the same time, so do you mean like concurrently? I think in that case, you would have to, because the thing is, there's only a single TCP channel and it is full duplex. So what you could do is on your server side, if you're intelligently sending audio data and combining it with text data, because again this supports both binary transmission for audio data, and then text data is already supported via UTF-8. So technically you could do that. The other solution would be to have two dedicated WebSocket endpoints. So one for audio and then one for text. It's in binary format. So that includes image data, because images and audio files, we represent them in binary format. So text is generally represented in some sort of textual format. So UTF-8 is an example, base64 an example for text data. But for image data, audio data, this is all in binary. So WebSockets support both. Okay, so there's another question. So, are there any other ways that a server can ping the client as the data changes on their own, so that there is no need for long connections? Wouldn't this be better than all the discussed solution if there is any? So there is another protocol called I think it's application layer protocol called web push. This is also, I believe, a newer protocol. Um, but I think underneath all this, it would you would still need some sort of persistent connection, because otherwise, I mean, otherwise you would have to initiate connections from the server side, and that's not something that we want to do. That's not something that's very feasible. So even with SEC, we do have event-based architecture. So SEC is not going to send data on that connection unless there is actually an event, unless data has actually changed. So web push, things like web push does build on top of that. But yeah, you would still need a persistent connection, to make sure that the server actually knows where to send that response. All right, so I'm just going to wait for a couple of minutes to see if we have any more questions, and then we can wrap this up. All right, so how many connections can a WebSocket handle at any time? Is there any limit? So one WebSocket connection includes one TCP persistent connection underneath it. So the number of WebSockets, aka the number of clients, would have to depend on how powerful your server is, how many resources your server is, what the implementation logic is. So it's not something that it's not a limitation on the WebSocket protocol. It's something that depends on how your server is configured. So I actually want to ask you guys, like, maybe in the chat, like, how many of you have worked with WebSockets? Which libraries have you worked with? What was the context you were working in, maybe, while you're waiting for more questions? So did you, in that case, combine both, like the data for text and the data for, did you like just push it all together and then send it together? Okay, so I see your top 3 to 5 tips for managing ongoing persistent WebSocket connections, please, like how to configure them. So on the server side, look, I think the easiest way is just to use a third-party library, because they're good. They handle things like reconnection. Because the thing with WebSockets is you would have to implement, if you were doing it from scratch, you would have to implement things like authentication yourself. That's not something that WebSocket protocol natively supports. So the easiest way would be to use some sort of use socket.io or Julia WebSockets. Yeah. So just work with that. All right. So work with socket.io was creating a business chat application using WhatsApp Business API used to send real-time responses to messages sent from the web app. Yep, that's a very valid use case for it. All right. I think let's end the workshop here. Thank you to everyone for joining. And again, we're calling this workshop 0 for a reason. We are going to, you know, based on the feedback that we get from you guys, we're going to, change up the message delivery and change up the overall process altogether.